In this video, we're going to do an example where we find the singular value decomposition of a matrix. So I'm going to start with a more basic example. And in the following video, I'll do a more complicated one. So let's say A is this matrix. If I want to find the singular value decomposition, what we do first is we find the orthogonal diagonalization of A transpose times A. So let's write down A transpose times A. So this matrix transpose, so I'd keep the negative 2's there on the diagonal. The 3 would go down here, the 0 would go up there, so that's going to multiply A. So negative 2, 3, 0. And if we multiply these two matrices, I'm going to do this quickly. We end up with 4, negative 6, 13. So now let's find the eigenvalues. So let's look at the determinant of A transpose A minus lambda I. So that'll end up being the determinant of, subtract lambdas from the diagonal. So 4 minus lambda, 13 minus lambda, everything else stays the same. So negative 6, negative 6. And if we multiply these two diagonal entries, we will get lambda squared minus 13 lambda minus 4 lambda, so minus 17 lambda, and then plus 52. And then multiplying these two, we get 36. So we subtract 36. All right, so now let's set this equal to 0. So let's set lambda squared minus 17 lambda, and then we get 16 plus 16 equals 0. So now factoring the left-hand side, we get lambda minus 1 times lambda minus 16 equals 0. So we know what the eigenvalues are. So we know lambda equals 1 and lambda equals 16. So next we need to get the eigenvectors. So I've gone ahead and done that. I've gone ahead and found the eigenvectors for each of these. And I've gone ahead and normalized them. So because A transpose A is orthogonally diagonalizable, I should be able to find an orthonormal basis of eigenvectors. So I've gone ahead and found those. Okay, so we are on to our next step. So at this point, I would have enough to set up the full orthogonal diagonalization if I really wanted to. But what I really cared about the most was getting an orthonormal basis of these eigenvectors, these VI's. And we've done that. All right, so step 2. So next, we want to list the eigenvalues of A transpose A in descending order. So where lambda 1 is largest and lambda n is the smallest. And then find the singular values. So remember, the singular values are going to be the square roots of these eigenvalues. All right, so the largest eigenvalue, lambda 1, is 16. That's the larger out of 16 and 1. And the smaller one is 1. And then I have to square root both of these. So to get my singular values. So sigma 1, my first singular value, is root 16, which is 4. Sigma 2, my next singular value, is the square root of 1, which is 1. So these are the singular values. So that's it for step 2. Step 2 is pretty quick. So we are ready for step 3. Now let's construct the matrix V. So the columns of V are the vectors Vi. These were the eigenvectors of A transpose A. So, and I'm going to order these so that Vi corresponds to the ith greatest eigenvalue. Okay, so when I write V here, we're going to have two vectors. There were two eigenvectors. So the first column, V1, will correspond to the greatest eigenvalue, which was 16. And the singular value that went with that was 4. Let me just call it sigma 1. That was 4. And then I sort of go in descending order of the eigenvalues. The next biggest eigenvalue was 1. And its corresponding singular value, sigma 2, is 1. Okay, so what was the eigenvector that went with 16? It was 1 over root 5, negative 2 over root 5. And the eigenvector that went with 1 was 2 over root 5. 1 over root 5. All right, so we formed our matrix V at this point. This is an orthogonal matrix. Now let's form sigma, because we already got the singular values. We are ready for step 4, and that's forming sigma. All right, so we want to construct sigma. So recall that when we construct sigma, D, the diagonal portion of sigma, is going to have the singular values, the sigma i's, along its main diagonal, and then we're going to put zeros everywhere else in sigma. So the general form for sigma is going to look like, we'll have a diagonal matrix up in the top left. And the diagonal matrix is going to be R by R, where R stands for the rank. Okay, and then everywhere else we're going to have a zero matrix. So zero matrix here, zero matrix here, zero matrix here. And the whole thing is going to be an M by N matrix. So that means that there are M rows. There are M rows here. And in this first diagonal portion, there are R rows, which means where this 0 is, there needs to be, I'm sorry, it just jumped. There needs to be M minus R rows for that. It'll have the same number of columns that this D did. It would have R. Okay, so that's the size of that submatrix. If I look at this one in the top right, that is going to have the same number of rows that this matrix had. It had R rows. This one's going to have R rows. How many columns will it have? Well, the whole matrix is n columns. D has R columns. So that leaves n minus R columns here. So now this matrix at the bottom right corner, that needs to have the same number of rows. It needs to have the same number of rows that this matrix had, so M minus R, and the same number of columns that this matrix had, so by N minus R. Okay, so in general, sigma is going to look like this, where this diagonal matrix D has the non-zero singular values along its diagonal. So, okay, so let's write this for our specific example. So in our example, sigma equals, so our largest singular value was 4, the next one is 1, and at that point, it's actually it. There's actually nothing else. Everything else is 0. So we actually don't have any of these other submatrices of just all zeros. It's just the diagonal portion. That's because sigma needs to be the same size as A. So that made this matrix square just like A was. And the other reason why is it has to do with the fact that R in our example was as big as it could be. The rank was 2. So that makes all these other sort of submatrices not appear here. But the next example I'll do in a future video will involve something more complicated here. All right, so we have one more step. So the last thing we have to do is construct the matrix U now. So the first R columns are going to have this form. So for example, the first column is 1 over sigma 1 times A times V1. So this whole thing equals the vector U1. And then up until the rth column still has that form. So actually, let me put this a little bit more to the side. So this whole thing is the vector U1. So where that comes from, so we saw that right before our proof of the singular value decomp theorem. So let's scroll it up. That was here. We saw, actually no, it's easier if I point it out here. Ui equals 1 over sigma I times A times Vi. That's true whenever I is in between 1 and R. So that's where it's coming from in our argument here. So U1 up until UR are going to be formed using that formula. And then after that, we may have more columns in U. We need to have enough columns to make a basis for Rm. So those vectors, UR plus 1 up until UM, they're any vectors that would just guarantee that this matrix has orthonormal columns. And of course, it's got to be square. Okay, so after we form this matrix U, then we're going to form A in this singular value decomposition. All right, so let's begin by writing down what the vectors U1 up to U are. So in our problem, U1, where'd it go? Okay, so there it is, U1. I don't know, it just disappeared there. U1 is 1 over sigma 1 times A times V1. So our first singular value, the largest one, was 4. So that's going to multiply A. A was the matrix -2, 3, 0, -2. And V1, the normalized eigenvector that went with the singular value 4 was, this one was 1 over root 5, and then -2 over root 5. So you should check this, but when we multiply this all out, we end up getting -2 over root 5, 1 over root 5. All right. So it's just a coincidence here that it just switched these two entries. In general, that will not necessarily happen. Okay, so now let's also write down U2 in this way. So we'll get 1 over sigma 2 times A times V2. So the next biggest singular value is 1, and that's going to multiply my matrix -2, 3, 0, -2. And then the eigenvector that went with this singular value, 1, was 2 over root 5, 1 over root 5. And you should check this one as well, but if I multiply this out, we end up with a -1 over root 5, and then -2 over root 5. All right. So now let's think about, do we need to get any more columns? Do we need to get like these UR plus 1 up until UM? So there's one quick way to tell just by looking at it. So my vectors, these U vectors, each have 2 entries. And we have 2 of these vectors now. We have U1 and we have U2. So they are already a basis, an orthonormal basis. So we don't need to get more vectors. I could also see that by looking at the sizes of my matrices. So I know A is 2 by 2. And however many rows A has, that corresponds to the size of U. So U is also going to be 2 by 2. However many columns A has, that corresponds to the size of V. V would be 2 by 2. And then sigma is always the same size as A. So sigma in this case would be 2 by 2. But the fact that U is 2 by 2 and we already have 2 vectors to put into U means we don't need any more. So in our problem, we have enough vectors for all the columns of U. All right, so we are ready to write down our singular value decomposition. So A is going to be equal to U times sigma times V transpose. So the columns of U we had up here, they were -2 root 5 first, over 1 root 5. And then the next column is -1 root 5 over -2 root 5. That's U. Times sigma, we already had sigma, that was 4, 0, 0, 1. And then times V transpose. So let's remind ourselves what V was. So let's scroll to where V was. So here was V. Let's just copy this so we can use it as a reference. All right, so I've written V there. We just need to transpose this. So the first row here, first row will become the first column. So we get 1 over root 5, 2 over root 5. Then the second row will become the second column. So -2 over root 5, and then 1 over root 5. And that is our singular value decomposition right there. So like I mentioned before, this was an easier example of a singular value decomposition problem, but they can get more complicated the larger my matrix A gets, and in particular, if when we form U, when we write these vectors U1, U2, and so on, If we don't have enough to get a basis for Rm, it gets a little bit more complicated. But we'll talk about how to handle that in a future video.